Disciplinary session. Okay, good afternoon, everybody, and thank you very much for coming to this plenary session. This plenary presentation, which will be given by Amitabh Basu. Really, it's a very good, very great pleasure for me to introduce Amitabh. Amitabh is really one of the pioneers in combinatorial optimization. Amitabh is a professor in applied mathematics and computer science in John Hopkins University. Amitabh got his PhD in Carnegie Mellon University under the supervision of Gerard Corniojolis. Carnegie Mellon University and the group of there is a very great group there with Gerard Corniojolis, Ravi, and Egon Baras died unfortunately in 2018, and many other nice researchers, nice people. Amitabh, his research is in combinatorial optimization, in integer programming, mathematical programming in general, but with particular application in operation research and data science. So he's one of the known people in now combinatorial optimization or mathematical programming and data science. Amitabh has already published more than 60 papers in really very high standard journals like mathematical programming, like mathematics operation research, discrete optimization, etc., and also in many famous conferences like SODA, like IPCO, etc. Amitabh is associate editor in mathematics operation research and in discrete optimization, and he has acted as a member of the program committee of several conferences, in particular in a very famous and very nice conference which is called ISCO. ISCO. So Amitabh helped us in 2 years, in 2018 and 2020. Really, we are, Amitabh, we are really honored today to have you with us for this presentation, and we would like, and I would like on behalf of the organizing committee, really to thank you very, very much to have accepted our invitation. Thank you again. Thank you very much. Amitabh today is going to talk about concrete complexity bounds for optimizing over integers. Okay, thank you, Amitabh. It's for you now.
Ridha, the honor is really all mine. It's a fantastic opportunity for me to come and speak to all of you, talk about some relatively recent work that I've been doing. But it's thank you so much for this fantastic introduction. I don't know if I deserve it. Thank you. Okay, so this is joint work with two colleagues of mine in Italy, Michele Conforti and Marco De Suma, and a PhD student, Hongyi Jiang, at Johns Hopkins University, where I teach. Okay. So just to set the stage, I'm going to talk about optimization problems of the following type. We are trying to find the maximum value of a linear function given by this objective vector C in that direction. And we have two kinds of constraints, right? So one type of constraints is convex constraint. So X is constrained to be in some closed convex set P. And then we also introduce some structured non-convexity. Throughout the talk, you can think about this as the mixed integer lattice. So some of the variables have to take values in the integers. So that's the first N1 values that you see here. I hope everyone can see my cursor on the screen. And then the rest can be continuous. So that's how, with this set capital S, I'm modeling the non-convexity, okay? But most of the talk will be focused on the mixed integer lattice. So basically integer optimization. Some theorems apply to more general non-convexities. I'll try to make that clear later, okay? By the way, I'm gonna take it reasonably slow so that I'm able to explain whatever I'm talking about as best as I can. So feel free to jump in with questions at any point in time, okay? Okay, so there are many ways you can sort of think about how to solve this problem. I am not going to focus on all of them. I'm really going to focus on two very classical algorithms. One that is based on something called cutting planes. I'll explain what this means. And the other one, which is based on branch and bound. I'll also explain what this means. And in practice, it turns out that neither method, if you just use one method, so just cutting planes or just branch and bound, they don't really solve industrial scale problems. Okay, so if you have really large scale problems, especially in modern applications today, just using branch and bound or cutting planes is not going to really solve the problem. But combining them into something called branch and cut is much better. It's orders of magnitude much more effective. And all the solvers today that solve mixed integer programming, they use branch and cut essentially. Okay, if you turn off any one component, it just can solve much smaller scale problems. So the goal behind all of this research that we were doing is to understand this phenomenon quantitatively. Why is it that individually these methods don't really work so well, but when you combine them, they suddenly perform magically? Okay, so what can we explain this a little bit more theoretically? Can we explain what kind of combinations actually lead to such improvements? Okay, so that's the basic goal. So now let me try to define what these things are, right? Okay, so a cutting plane is something very simple. It's a half space or a linear inequality that is valid for all your feasible points, right? So P intersect S is all your feasible points. And it's called a non-trivial cutting plane if you actually shave off something from your convex relaxation. Okay, very simple. And what is a cutting plane algorithm? Well, you start with your initial convex relaxation, P, and you just solve the convex optimization problem. For now, forget about the non-convexity. You get a point xi at every iteration, 0, 1, 2, so forth. You get your optimal solution. If it satisfies the non-convexity, then clearly that's the optimal solution. You stop and you report that. Otherwise, you find some cutting plane that cuts it off, and you add that new inequality, that cutting plane, into your convex relaxation, and you iterate the process. Okay. So one thing here that we should keep in mind is something called a cutting plane paradigm, meaning this is some strategy that you use to generate your cutting planes during this procedure. Okay, and there are many different ways one can do this. There are things called Quatal-Gomery cutting planes. There are things called split cuts. There are things called mixed integer rounding cuts, Gomery cuts. There are a lot of different ways one can generate this. Right now, I'm keeping this abstract, and I'm saying that, okay, I have this kind of a function, script C, that given any convex set, it can report a family of cutting planes for me to choose from that I can add at this stage. Okay, very simple. Okay, so here's a simple illustration of this, how this goes. Ignore that pink thing. If you know split cuts, then that pink thing will make sense, but otherwise forget about that. So this polygon here is your convex relaxation, and you are interested in finding the best integer point in this region. And this blue line here is a cutting plane. It shaves off a little bit of your polygon, but it does not shave off any integer point that is of interest. Okay, so you introduce this cutting plane, you get a new polygon. That's the new convex relaxation. Then you again solve the convex optimization problem, you add another cutting plane, and you get a new convex relaxation, which is this red thing. And you keep iterating until at some point, your optimal solution is an integer point. Okay, that's what a cutting plane algorithm is. Okay. What about branch and bound? Well, it's based on this idea of a valid disjunction. Okay, so a disjunction with respect to your non-convexities, in this case, the mixed integer lattice, is just a union of closed convex sets, such that all of your integer points are covered by these closed convex sets. So a very classical disjunction is something called a variable disjunction. What is a variable disjunction? You take an integer variable, xi, and you say xi is either less than or equal to k, or xi is greater than or equal to k plus 1, because all integer points will satisfy one of these inequalities. That means this union of half spaces, xi less than or equal to k, xi greater than or equal to k plus 1, that's a valid disjunction. Okay, so it's a two-term disjunction, but you could have more disjunctions. There are more complicated disjunctions that are discussed in the literature. Okay, a generalization of the variable disjunctions is what is called split disjunctions. Split disjunctions basically take two, again, it's a union of two half spaces that cover all your integer points, but they don't have to be aligned with the coordinate axes. Okay, you can take any two parallel hyperplanes such that the two half spaces cover all integer points. Okay, so these are two-term disjunctions, but you could have, like I said, more complicated disjunctions. And a branch and bound algorithm based on a family of disjunctions is the following. You start with your initial convex relaxation, and you start dividing it into smaller subproblems based on valid disjunctions. So basically, if I take your initial relaxation and I have a valid disjunction, let's say a variable disjunction, that separates the problem into two parts, and then I will solve those two subproblems recursively, and then take the best of those values. Okay, so hopefully most of you are familiar with what branch and bound does. I've stated it here in a very formal way. The one thing that maybe you want to keep in mind is that you always keep something like a lower bound to prune away certain subproblems that you know can never contain the integer solution. Okay, so again, I have a quick illustration here. So here again, I have my polygon. And as you can see, these pink regions denote two half spaces. So this half space is denoted by this pink region, and this half space is denoted by this pink region. So this is what I was talking about when I was describing split disjunctions. Now, if I intersect my initial polygon with these two half spaces, then I end up with two smaller subproblems, right? And if I solve both of them and I pick the best of those values, then I get my integer solution. And I can keep track of this by keeping a tree, which is called a branch and bound tree. This initial root node corresponds to the original relaxation. And then when I break it into two problems, those are the children of those problems. Now, let's say on this subproblem, I apply this four-term disjunctions. As you can see, I've got four cones here, translated cones. Together, they cover all integer points. There are no integer points in this region, in the union of these two strips. And so now I can divide this subproblem into four new subproblems. One of them, of course, happens to be empty, but I won't know that unless I process that problem with all those constraints. And the linear programming algorithm will tell me that it's actually an empty set. So as far as the tree is concerned, the tree will have four new children. One of them is infeasible, and three of them are feasible. And then you kind of keep going. And like I said, if at any point when you process a problem and you solve the convex optimization problem and it gives you an integer point, then that might update your lower bound because this is a feasible point, and that may prune some of these other nodes. Okay, so hopefully now cutting plane and cutting plane algorithms, branch and bound algorithms are clear. Any questions? Okay, good. So one thing that's interesting to note is that actually a disjunction can also be used to generate cutting planes. Okay, how does this work? Well, Any disjunction covers all your integer points or all your non-convexities. So if I take any half space that is valid for the intersection of my relaxation with all of these, all of the terms of the disjunction, then certainly this half space will be valid for all the integer points inside this convex relaxation, right? So as an example, let me go back to this picture here. You have this convex relaxation, this polygon. I have a valid disjunction, which is now in this case a variable disjunction. Okay, so x1 is less than equal to this integer value, x1 is greater than equal to this integer value. And this blue linear inequality is actually valid for both this part of the relaxation and this part of the relaxation. Since all the integer points are in one of these parts, that means that this blue line is a valid cutting plane. So any disjunction that you can think of can actually generate valid cutting planes if you can generate inequalities valid for all the different parts of your relaxation given by the disjunction. Okay, so this is something good to keep in mind, that disjunctions can not only lead to branching, but can also lead to generation of cutting planes. So you can design a cutting plane paradigm based on a family of disjunctions. Okay, and what is branch and cut? Well, branch and cut just combines these two ideas together. So you do what you were doing in branch and bound, and at any sub-problem that you're processing, you're allowed to add new cutting planes. In particular, you can add local cutting planes because you now have a smaller sub-problem. You may generate some cutting planes based on some cutting plane paradigm that is valid for that sub-problem, so that you kind of strengthen that sub-problem, and then you could continue with branching. So the only thing that has happened here is this new extra step where you make a decision whether you want to branch or you want to add a cutting plane, right? So at this point, you've solved the convex optimization problem. It's not an integer point, so you could add a new cutting plane, or you could decide to branch further at that point. So that's branch and cut. Okay, very simple. So how do we measure efficiency? We want to talk about, okay, when does branch and cut become better than branch and bound or cutting planes? Well, the main computational overhead is really the solution of the convex optimization problems or the linear optimization problems, right? So in cutting planes, you have a relaxation, you solve the relaxation with linear optimization or convex optimization, and then you decide to add cutting planes or not, right? Or in branch and bound, at any sub-problem, you first solve the convex problem, and then if you don't get an integer solution, then you decide to branch or you decide to add cuts or whatever you do. So really, you want to minimize the number of linear programming calls that you make or convex optimization calls that you make. So there are two aspects to this. One is, like I said, the number of linear programs. But of course, it could be that in certain situations, you solve more linear programs, but they are much easier linear programs than if you had solved a smaller number of linear programs, which were more complicated. Okay. So you also want to keep track of how complex the linear programs are, because you may want to trade off the number with complexity. Now, it's notoriously hard to decide what's the quantitative measure of complexity for a linear program. Okay, maybe it's the number of constraints you have, maybe it's something else. So what we focused on was something called the sparsity of the constraints of the linear program. It's kind of a well-documented fact that if you have a linear program and each constraint has lots of zeros, or the constraint matrix is kind of sparse, then these programs are relatively easier to solve and also don't suffer as much from numerical instabilities because of the simplex methods, basis calculations. So that's what we concentrate on. Okay, and essentially what we are going to try to do is figure out when these algorithms, branch and cut, branch and bound, cutting planes, how they perform with respect to these measures. Okay, so for this, suppose I want to show that, okay, here's a family of instances where branch and bound really does really well, but cutting planes don't do well. How am I going to show that cutting planes don't do well? I have to give you a lower bound on the number of linear programs you have to solve, or the complexity of the linear programs that show up, right? So for this purpose, something called a proof is actually very important. Okay, so what is a cutting plane and a branch and bound proof? Well, you want to show the validity of some inequality. So if, let's say, C here is the objective vector that I had defined, then gamma can be any upper bound that you want to show on your linear objective. Okay, so maybe gamma is the optimal value itself. Then you want to show that no solution can do better than this optimal value. So this will be a proof of the optimality of the current solution. But this, you can think of proofs as proofs of validity of any valid inequality. They may not even be related to the objective function. Okay, so suppose you have some valid inequality, Cx less than equal to gamma, for your feasible solutions. Then a cutting plane proof of this, of the validity of this inequality, is the following. You basically show a sequence of cutting planes, H1, H2, Hk, such that when you add them in sequence, this inequality becomes valid for the final relaxation. Okay, so if you think of, again, the proof of optimality, if you can give me a sequence of cutting planes so that the final polytope satisfies Cx less than equal to opt, then you know that nobody can do better than that value opt. Okay, similarly, a branch and bound proof is something like this. So you have that tree that you have created, and now suppose you know that all the leaves, which are the current sub problems that you need to process, the leaves of that tree, suppose this inequality is valid for those leaves, then you know that no solution in the original problem can do better than this gamma value with respect to C. Okay, so that will be a branch and bound proof of validity or optimality and so forth. Okay, and the main point of defining these proofs is that if you have a cutting plane algorithm or a branch and bound algorithm or a branch and cut algorithm, then it automatically gives you a proof, because think of the cutting plane algorithm. It generates some cutting planes, and that sequence of cutting planes automatically gives you a cutting plane proof. Okay, so if you prove a lower bound on the size of cutting plane proofs or branch and bound proofs, that gives you automatically a lower bound on the efficiency or the number of linear programs that a cutting plane algorithm has to solve or a branch and bound algorithm has to solve. Okay. In the case of the branch and bound algorithm or the branch and bound proof, the size of the proof is the number of nodes you have generated or the number of leaves equivalently. Any questions so far about why I'm talking about proofs? They are going to be basically a tool for establishing lower bounds on the number of linear programs that a cutting plane algorithm or a branch and bound algorithm has to solve. Okay. Okay, so here's a summary of the results that we have when I just try to compare cutting planes with branch and bound. I'm going to talk about branch and cut in a few minutes. But before I can understand what's going on with branch and cut, I want to understand how these two methods compare against each other. Once I understand their relative strengths and weaknesses, then I can try to figure out what makes the combination powerful. Okay. So here, let me try to explain a few things. So what we try to first do is, okay, if I have a very powerful cutting plane paradigm, and my branch and bound is based on some very simple disjunctions, then it kind of intuitively feels that obviously the cutting plane paradigm will dominate branch and bound because you're giving cutting planes a lot of power, right? Taking a very extreme example, suppose you had a magic oracle for cutting planes that always generated all the inequalities that are tight at the optimal integer solution. That maybe you have some magic oracle like that, then you would solve the problem by just introducing those inequalities that are tight there. Those are the cutting planes you generate, and you always solve the problem in n steps, where n is the dimension. And any branch and bound algorithm can never hope to match that, right? So to kind of make the playing field level, what we decided to do was this. We're going to base both the cutting plane paradigm and the branching scheme. They're going to be based on the same family of disjunctions. Like I said, if I fix a family of disjunctions like variable disjunctions or split disjunctions, then they lead to a branching scheme for branch and bound, but they also lead to a cutting plane paradigm, right? So now I'm going to look at two different families of disjunctions. One is the variable disjunctions that I described, and the other one is the split disjunctions. So that's how these columns are partitioned according to whether I'm considering cutting planes and branchings based on variable disjunctions or cutting planes and branchings based on split disjunctions. And then I'm also going to distinguish between 0-1 problems where the convex relaxation is a subset of the 0-1 cube, and I'm really interested in the 0-1 points, or I'm maybe interested in more general integer programming with general convex sets and general integer points. Okay, so that's how the columns are partitioned. And now if I want to discuss complexity, the dimension can be part of the input. So I may allow the complexity to depend on the dimension. So I can reasonably talk about polynomial in dimension or exponential in dimension. Or I could keep the dimension as a fixed constant, like I'm only considering problems in dimension 10, 15, some fixed constant. And the polynomiality or the exponentiality is really dependent on the bit complexity of the problem size. Okay, so that's how I distinguish between the rows. Okay, so now let me try to explain what's actually inside these boxes. So in the first box, where I'm looking at allowing dimension to be a variable, to be part of the input, and I'm looking at 0-1 problems and variable disjunctions. So by the way, if I look at 0-1 problems and variable disjunctions, cutting planes based on this are called lift and project cuts. So these are cuts like Shirali-Adams cuts that you might have heard of. And there are other lift and project cuts that exist. In this case, what one can show is that cutting planes always dominate branch and bound. Okay, what's the precise statement? Here's a precise statement. Suppose I have a 0-1 problem and I'm focusing on the family of variable disjunctions. If there is a branch and bound proof or algorithm that shows that, okay, here is a upper bound on the objective, or here's a proof of validity of this inequality with size k, the proof has branch and bound proof has size k, then for any epsilon, if I sort of add a slack of epsilon, I can generate a cutting plane proof with the same length k, okay, or better, okay. By the way, if I look at only the linear case, so the convex relaxation is really a polytope, then we can get rid of the slack. So the slack is really needed for more general convex sets, okay. So this is the notion by which I mean that cutting planes are always better than branch and bound, because if a branch and bound algorithm solves it in k steps, then there is a cutting plane algorithm that will also solve it in k steps, okay. And we strengthen this by showing that it can actually be exponentially better. So we find a family of stable set problems. In this case, it's basically the stable set on a union of n triangles, but there are many other examples that we create in the paper. And we show that actually this problem can be solved in order n steps with a cutting plane algorithm based on lift and project cuts. However, any branch and bound proof of optimality is exponential sized. Okay. So this is a concrete example where cutting planes are always better than branch and bound. And in some cases, like the stable set instances, they can be exponentially better. Okay. Okay. So if we move away from the 0-1 scenario, then actually this advantage of cutting planes disappears. So again, I'm still basing on everything on variable disjunctions, both the cutting planes as well as the branching. But now there are instances where branch and bound can solve the problem in constant time, where cutting planes take infinite amount of time, or if you are allowing epsilon slack, then they need at least poly 1 over epsilon number of steps. Okay. Okay, so I had this example to show you that, but maybe since I'm running maybe a little bit low on time, I'm going to skip this example. Okay, so now if we move away from variable disjunctions to split disjunctions, so now both the branching is allowed to use more general splits, not just variable branching. But my cuts are also based on split disjunctions. So these things are called split cuts. Okay, they were introduced by Cook, Kanan, and Schreiber in the early 90s, and they are a very important family of cutting planes. Now it turns out that the situation completely reverses. Once you give branch and bound this power of using general split disjunctions, it actually dominates split disjunctions always. So what's a more precise statement? Well, basically, if you have any cutting plane proof or algorithm of length k for some inequality, then there is also a branch and bound proof and algorithm that proves the same inequality with a blow up of at most a factor of 3. Okay, so within constant factors, branch and bound proofs can do exactly what cutting plane proofs can do if we are talking about split disjunctions and split cutting planes as split cuts. Okay. So that's what I mean by BB less than equal to CP. This is up to this constant factor of 3. Okay. In the 0-1 case, we are not sure whether there are instances where you can prove polynomial versus exponential gap or even a strict gap. But at least in the general non-0-1 case, we have a family of examples where you can prove gap of constant versus polynomial. So branch and bound can be at least, I guess, exponentially better if you consider constant versus polynomial, but it's really constant versus polynomial. Okay. Okay. Now it also turns out that if you go to the fixed dimension case, so now dimension is a fixed constant. So I cannot really say polynomial in dimension or exponential in dimension anymore. Then, of course, the 0-1 case becomes trivial because there are only constant number of points to sort of enumerate, and both cutting planes and branch and bound can do this very, very quickly. So they're both order 1. But if you go to general convex sets, then this starts to make a little bit more interesting scenario. And in this case, again, you can show that branch and bound is as good as cutting planes up to polynomial factors. Okay, so again, these less than equal to's, they hide polynomial factors, except for this case here, where it was really at most as large as the branch and bound proofs. Okay, so to make this statement precise, what I need to do is define something called the size of a disjunction. So any disjunction is a union of closed convex sets, right? So if any of the closed convex sets is non-polyhedral, then the size of the disjunction is infinity. Otherwise, if all of the terms are polyhedral, like splits, there are just 2 half spaces, then the size of the family is the number of half spaces I need to describe all of these terms. Okay, so in the case of split disjunctions, the size of the disjunction is 2, okay, because I just basically need 2 half spaces to describe the entire disjunction. And if I have a family of disjunctions, then the maximum size of the disjunction in the family is the size of that family. Okay. Okay, so once I make this definition, then one can show that if you focus on a family of disjunctions whose size is bounded by some constant m, so m is a constant. So for example, splits, m equals to 2. Okay. And in this case, actually, S can be an arbitrary non-convexity, doesn't have to be the mixed integer lattice, but let's think about the mixed integer lattice for now. Then we show that if you have a cutting plane proof or algorithm of length k, then there is a branch and bound algorithm that has this complexity. So m is the size of the family of disjunctions. So in the case of splits, this will be 2. K is the size of the cutting plane proof. And n here is the dimension. So if dimension is fixed, it's a fixed constant, then this is a polynomial factor of this cutting plane proof. So that's what I really mean when I say that branch and bound is as good as cutting planes up to a polynomial factor. Okay, and we can also give examples where they show that, you know, branch and bound can be much better. If you focus on just the variable disjunctions, then the gap is constant versus exponential. Okay, there are examples like that. But if you go to split disjunctions, then the gap is constant versus polynomial. Okay, so still strictly better, but not as drastic as constant versus exponential. Okay, any questions about these results of comparing pure cutting plane algorithms versus pure branch and bound algorithms? We haven't really combined them yet. We have tried to understand their relative weaknesses and strengths so far. But any questions about this table? Okay, good. So now let's get to this main question. When is it, if you give me a cutting plane paradigm and you give me a branching scheme, when is it going to be useful to combine them into branch and cut? Clearly, these results that we were talking about, they kind of show that in certain cases, one paradigm may completely dominate the other paradigm. For example, if you're looking at 0-1 problems with variable disjunctions, then you might as well just use cutting plane algorithms. Combining them is not going to give you much advantage, because whatever branch and bound is doing, you can also do with cutting planes. Or in this case, for example, branch and bound was dominating cutting planes. So again, intuitively, it feels like, okay, combining them in this case is not going to really help much. So clearly, when you give, or let me say it like this, when branch and bound, or the branching scheme and the cutting plane paradigm, they are based on similar information, it kind of seems like you are able to show one strategy dominates the other, and you're never really going to get much of an improvement with branch and cut. So that leads us to this definition. We say that a cutting plane paradigm and a branching scheme are complementary. So by the way, branching scheme, I just mean a family of disjunctions. That's all that means. They are complementary if there is a family of instances where the cutting planes do much better, meaning that they give polynomial size proofs, whereas the branch and bound proofs are exponential. You have a family. So that means that branch and bound does not dominate cutting planes on this family. And there is another family where the situation is reversed. Okay, so branch and bound does polynomially well, whereas cutting planes take exponential time. So what are we saying? We are saying that complementary pairs of cutting plane paradigms and branching schemes are those where neither method dominates the other, because there's a family of instances where cutting planes are much better, and there is another family of instances where the branching scheme is much better. So intuition is that only in such a situation can you really say that combining them is going to give you an advantage. Okay, if you have a scheme, a cutting plane paradigm and a branching scheme, where for every instance the cutting plane always does as well as the branching, then probably you're not going to get much by combining them. And so the formal theorem we are able to show is that indeed, if you have a branching scheme and a cutting plane paradigm that are complementary, and they satisfy some regularity conditions, this is just to make the theorem work, but every branching scheme in the literature and every cutting plane paradigm in the literature satisfy these regularity conditions. So they are really mild conditions. We had to make some formal statements to make everything work out mathematically, but in practice, these conditions are always satisfied. Okay, I cannot think of any reasonable branching scheme or cutting plane paradigm where these conditions would not be satisfied. Okay, so you can really, this is basically without loss of generality. Okay, but to be formal, we have to have these conditions. I'm not going to describe them. Okay, and we assume that the branching scheme at least has the ability to branch on variables. Okay, so you give they are not super simple branching schemes where you cannot even branch on variables. So suppose that branching has that ability. Then if you have this complementary pair, there exists a family of instances. We give a concrete construction where branch and cut proofs, so combining them into branch and cut, gives you polynomial efficiency. But you can say that the branch, if you have a pure branch and bound algorithm based on this disjunction family, that will take exponential size on this family. And any pure cutting plane algorithm will also take exponential size. So really, branch and cut is giving you an exponential advantage on pure cutting plane algorithms and pure branch and bound. Okay. And this happens when you have a complementary pair of disjunctions and branching cutting plane paradigms. Okay, so one may say, okay, maybe there are no pairs that really satisfy this definition of complementary pair. Maybe you have a bogus theorem that whose hypothesis is never satisfied. Well, there are these two very famous paradigms, the Quatal-Gomery cutting plane paradigm and the simple variable disjunction family. These are things that are used in modern solvers. You can prove that these two are actually a complementary pair. There is a family of instances where branch and bound does exponentially better based on variable disjunctions than Quatal-Gomery cuts. And there is another family of instances where Quatal-Gomery cuts do exponentially better than variable disjunctions branching. Okay, so there are this very commonly used pair of cutting planes and branching schemes are a complementary pair, and that gives some kind of theoretical justification why their combination works so well in practice, but on individually they can't really do much. Okay, so that's kind of the main punchline that we kind of arrived at. So far, we have been focused on the number of linear programs that we solve or the number of convex optimization problems we solve. We didn't really focus on the complexity of the problems, right? The sparsity of the constraints, like I said. So I won't have time to discuss everything that we know about this scenario. Let me just focus on pure branching, pure branch and bound. Here's a classic example from Jarrow's law. So here we are looking at a 0-1 problem where this left-hand side n is the dimension and it's odd. And since the right-hand side, the left-hand side, since it's an even number, there is actually no 0-1 point that can satisfy this equation. Okay, so this is an infeasible integer program. And Jarrow's law showed that any branch and bound proof of infeasibility based on variable disjunctions needs exponentially many nodes. So it has exponential size. However, there's a very simple disjunction that can prove infeasibility in just one step. The sum of the variables is less than or equal to this, and the sum of the, so this is a split disjunction. This is not a variable disjunction, it's a split disjunction, and that proves infeasibility in one step. So a branch and bound size of a tree of size 3. So exponential versus 3, if you change from variable disjunctions to split disjunctions. So if you think of the disjunction, the variable disjunctions as having sparsity 1, which is the number of non-zeros in your inequalities, right? Xi less than or equal to something, Xi greater than or equal to something. So only one non-zero coefficient in your disjunction. Whereas the general split disjunction is dense, then this, we can summarize this observation by saying that if you restrict sparsity to 1, then you need exponential size branch and bound proofs. But with unrestricted sparsity, you get a constant size. So then the natural question we had was, okay, what is the trade-off? Suppose I don't restrict to sparsity 1. Suppose I allow disjunctions with 2 non-zeros or 5 non-zeros. What kind of goes on in this question with respect to the size of the branch and bound proof? And it turns out that we proved that even if you go to a bigger constant than 1, you still need exponential size trees. Okay, and so the conclusion is that if you restrict sparsity to a constant, you still have exponential size trees, and to really get constant size trees, you have to go to essentially full density, okay, or linear density. We have a slightly more fine-tuned analysis of what happens when k gets closer to n over 2. You don't really get constant. You can still prove a super constant lower bound, actually a linear lower bound, but I won't get into that. Okay, let me skip cutting planes. By the way, this relationship between sparsity and the strength of cutting planes has been studied previously by De, Molinaro, and others. But let me just stop here with sparsity. So essentially, there's a lot to do here. You can try to figure out what happens to the efficiency of your algorithms once you make sparsity a parameter of interest. Okay, and once you sort of tweak this parameter, your complexity can actually change. And so there now arises this kind of tension between reducing the number of LPs you want to solve and the sparsity of the LPs. So if you increase the sparsity parameter, the number of LPs may be lower, but then your LPs are difficult to solve. So this, I think, there's a lot to explore here. We have only started exploring, I think, just the surface of this problem. Okay. So let me finish up with some open questions. Like I said, I think, yeah, there's a lot to do with regards to understanding the role of sparsity in the size of branch and bound proofs, cutting plane proofs, branch and cut proofs. We have some initial results, but there's a lot more to do. Okay. By the way, so I said that intuitively it feels that if I have a branching scheme and a cutting plane paradigm where one method always dominates the other, then combining them into branch and cut probably is not going to help. That's why we defined complementary pairs and showed that if a pair is complementary, then you get exponential advantage. But it would be nice to show the converse, that if you are getting an advantage, then the pair is complementary. Okay, then they must satisfy this. Then that would be a characterization of exactly when branch and cut has exponential advantage over pure branch and bound and pure cutting planes. Okay, so we haven't been able to establish it. It would be nice to establish some kind of a converse. We have some partial converse results, but this is in general totally open. Okay, like I said, I mean, there's this slightly small gap in this table where if you look at 0-1 problems and you look at pure branch and bound based on split disjunctions and pure cutting plane algorithms based on split cuts, then branch and bound is always better than cutting planes up to this factor of 3. But are there instances where the gap is strictly big, better than constant, right? So maybe branch and bound have polynomial size proofs and cutting planes have exponential size proofs. This we have not been able to establish in this case. Okay, and again, if you recall this result here, the 0-1 case with variable disjunctions, I showed that if you add this epsilon slack in the general closed convex set, then cutting planes always have a proof of the same size. And it would seem like that K here absolutely doesn't depend on epsilon. I'm generating the same size proof for every epsilon. So then I should be able to generate a cutting plane proof with epsilon equal to 0. Unfortunately, we are not able to establish this. This is a very strange phenomenon that for every possible epsilon, I get exactly the same size cutting plane proof. But for epsilon equals to 0, we cannot establish a cutting plane proof of that size. So that would be a nice little problem to resolve. I think the answer is that you should be able to do it, but I'm not able to establish this. So like I said, epsilon equal to 0, we did establish for polytopes, but the challenge is to do this for general closed convex sets. Okay, and I said that, if I have an algorithm that leads to a proof, and therefore lower bounds on proofs lead to lower bounds on algorithms, but like the P versus NP controversy, in the narrow setting of branch and bound or cutting planes, is there actually a difference between algorithms and proofs? So are there instances where there are small size proofs but there are no algorithms. Every algorithm is exponential efficiency. That would require establishing exponential lower bounds on algorithmic efficiency other than proof lower bounds. And I know of no way to do this. All lower bounds on algorithm efficiency go through lower bounds on proof sizes. So this would be a nice question to resolve, a sort of baby version of P versus NP, but restricted to branch and bound or cutting planes. Okay, I think I will stop right there. And I'll take any questions, comments. Ridha, I can't hear you anymore. I don't know what I did.
Okay, thank you very much, Amitabh, for this nice presentation.
Sure.
And I think we have time for 2 or 3 questions. Yes, yeah, we have time. So yeah, any question? Any question? Maybe I can start. Yeah. So you said that the complexity, I mean, one of the measure is the number of linear programs that are called to be solved within the resolution of the problem. Okay, but these linear programs maybe, I mean, I don't know, but maybe of high sizes, may take a lot of time to be solved. The packages have not the same efficiency, and so on and so on. So yeah, if the complexity is going to consist only in the number, maybe there is some biased, I mean, consideration here. Maybe, I don't know. How do you explain this, Amitabh?
It's a very good question. So we definitely have not been able to formalize the complexity of the linear programs in a very satisfactory way. Like I said, we decided to focus on the sparsity of the constraints. So if we have sparser linear programs, we say that these are easier programs. But one could also, again, like you said, look at the size of the program. How many constraints do you have? And there could be a trade-off there, right? We don't have that many results yet to say about this trade-off. Maybe you want to have a larger number of LPs, but a smaller size or smaller sparsity. There are some results, like I showed at the end, about this, but there's a lot more to do, I think, here. So it's definitely very important to firstly formalize what we mean by a linear program is more complicated than another linear program, and then use that to understand the trade-off between, okay, maybe a branch and bound scheme produces a lot of linear programs, but they are all easy linear programs. And I would prefer that compared to some branch and bound scheme which solves a small number, but they are all super complicated linear programs. And this has to be understood very well. And on that sort of Pareto trade-off curve, where you want to be is another very good question. There's a lot to do here. We don't have too many results yet, unfortunately. Yeah.
I see. Okay, thank you, Amitabh. Okay, any other question?
Oui, moi j'ai une question.
Oui, Ibrahim.
I have a question. Thanks for the presentation. In what you presented, you were talking about cutting planes, but if I understand well, you were dealing with, I mean, standard cutting planes. By standard, I mean split cuts, Gomery cuts, Mir cuts, yes, and so on. Does the result you presented here still works if we consider problem-specific cutting planes? For example, in some combinatorial optimization problems, when we are dealing with polyhedral investigation,
yes,
we are able to introduce some cutting planes. Maybe sometimes we are able to give a complete description of the right, convex hull of the polytope. So the results you have presented here are still working if we consider such kind of problem-specific cutting.
Not really, because we wanted to, so in the first set of results where I was just comparing cutting planes versus branch and bound, we really wanted to base both of them on the same kind of scheme so that they have both the same power. So now if you look at a specific problem like TSP and you just use branch and bound based on variable disjunctions, but you throw in for cutting planes comb inequalities and all kinds of inequalities, then it's conceivable that, you know, the cutting planes have a lot more power than just variable branching, and you should be able to do better. So to make a meaningful comparison, we had to base them both on the same kind of power, so they both have the same information. And so certainly this doesn't have much to say about specific problems like TSP or knapsack where you have problem-specific cuts. I will say that in this result, where we show that the branch and cut is much better if you have a complementary pair, this a priori applies to a specific example. If you can show that the branching scheme you are using, so let's take TSP. Suppose now I say I'm going to use split disjunctions, not just variable disjunctions, I'm going to use split disjunctions. And the cutting plane paradigm is all the cutting planes that you know for TSP. Suppose you can show that these two paradigms are complementary, meaning there are certain TSP instances where the cutting plane algorithm is actually going to do exponentially better. And there are certain other TSP instances where branching on splits actually is going to do much better than all these cutting planes that you know for the problem. If you can establish this, then you know that there are in TSP instances where branch and cut will be exponentially better than pure cutting planes and pure branch and bound. Okay. So this one would apply to your scenario as long as you can establish complementarity.
Okay.
But that's a great question. Thank you.
Okay, good. Thank you.
Thank you. Other questions? Other question? Okay, we are on time exactly. Amitabh, really thank you very, very much again for your presentation. Really, it was very, very interesting, and it was really a very nice moment.
Thank you, Rida. Thank you for your invitation. It was a real pleasure and a real honor.
Thank you very much. Okay, now let's go to the next presentation by Boris